So I'll be redoing problem 2 of the exam, and for part A, it wants us to draw the velocity profile, and we're going to assume a no-slip boundary condition, which means the velocity of the slurry at the surface of the belt will equal the velocity of the belt itself. And my first mistake was assuming the velocity at the atmosphere would be 0. It is not. It is actually the shear force that is 0, because the viscosity of the air is negligible compared to the viscosity of the water. So the velocity profile should actually look like this, where it is the velocity gradient that is 0, and not velocity itself. And then for part B, we need to find the velocity in x direction, and the equation for it. And we're going to start with the Navier-Stokes because it is solid state. It's not changing time. That means this is 0. Fully developed means it doesn't change if you go up or down the stream. So this is 0. We're going to assume parallel flows. So it's all the layers are moving parallel. So this is 0. And then no edge means the thickness of the slurry does not matter. So this is 0. And because this is gravity driven, there's no pressure gradient. So this is 0. And because this is 0, this has to be 0. And then because this is 0, this has to be 0. So then we are just left with shear in the x due to the change in y is only because of the force of gravity, which is rho g sine theta over mu. So then we can integrate twice to get our velocity equation, and then we have our two boundary conditions where we assume the velocity when y equals 0 is equal to the belt, and then we can assume the shear when y equals h is equal to 0. So then once we have those two boundary conditions, we can plug them to get C1 and C2, and then we can get our velocity equation. So then for part C, we have to find the minimum velocity so that all layers have a positive velocity. This is where I made a mistake, another mistake, because I assumed it was like the net velocity had to be greater than 0 and not like each layer had to be above 0. So here I integrated when really I need to do was find where the velocity is at a minimum, and that happens to be at the surface. So when y equals h, and then all you have to do is set that equal to 0, and then you can just plug in h for your equation, and then this is what your minimum belt velocity has to be. And then for part D, it's just a physical explanation, which I said the minimum belt speed required is proportional to the square of the slurry thickness h. As thickness increases, the mass of the fluid increases linearly. For a thicker layer, because momentum is transferred from the bottom due to viscous forces, the belt must go significantly faster, specifically h squared, to overcome the cumulative weight of all the layers of fluid above it.